The nearest star beyond our Sun is so close that its light reaches your eyes in just over 4 years. Astronomers call it a neighbor. Science fiction calls it a destination. Every article about humanity's future among the stars points to it first. Alpha Centauri, 4.37 light-years away. In cosmic terms, it is right next door. But here is what nobody tells you. That front door opens onto a hallway so long, so dark, and so hostile that no propulsion system ever built or even seriously proposed could carry a human being to the other end within a single lifetime. The fastest object humanity has ever launched would need over 70,000 years just to coast there. The nearest star is not close. It is a wall dressed up as a window. If you enjoy going deep on the science most people never hear about, hit that like button and subscribe. It genuinely helps this channel keep doing what it does. Are you comfortable? Let's begin. Every civilization that has ever looked up at the night sky has done the same thing. It has picked the brightest points of light and drawn meaning from them. Stories, navigation, calendars, and gods. But there is one point of light that carries a weight no ancient storyteller could have understood. One system, one tiny clutch of stars that has become the single most important object in the modern imagination of the human future. Alpha Centauri. If you live in the southern hemisphere, you have probably seen it. It is one of the brightest objects in the night sky, visible to the naked eye from latitudes below, about 29 degrees north. Burning in the constellation Centaurus with a steady white-gold glow that makes it look close. And in a cosmic sense, it is close. It is the nearest star system to our own sun. That sentence has shaped more dreams, more mission proposals, more science fiction novels, and more casual assumptions about humanity's destiny than almost any other fact in astronomy. But that sentence is also one of the most dangerous lies in science. Not because it is wrong, it is technically correct. Alpha Centauri is the nearest major star system. The danger is in the word nearest. Because nearest, in this context, does not mean what your brain thinks it means. It does not mean reachable. It does not mean close. It does not mean anything resembling the ordinary human experience of distance. It means least impossibly far. And the difference between those two ideas is the entire subject of this story. Let us start with what Alpha Centauri actually is, because most people, even people who know the name, have only a vague idea. Alpha Centauri is not a single star. It is a system of 3 stars bound together by gravity. The first two, Alpha Centauri A and Alpha Centauri B, are a binary pair. They orbit each other roughly every 80 years at distances that range from about 11 to 36 times the distance between Earth and the Sun. Alpha Centauri A is a G-type main sequence star, the same category as our Sun, but slightly larger, slightly brighter, and slightly hotter. Alpha Centauri B is a K-type star, smaller and cooler, but still a proper star in every meaningful sense. Together, they form a pair that would look like a single brilliant point to anyone watching from Earth without a telescope. The third member is the one who changed everything. Proxima Centauri is a tiny red dwarf star, far dimmer than the other two, orbiting the binary pair at an enormous distance of roughly 13,000 astronomical units. That distance is so large that Proxima takes hundreds of thousands of years to complete a single orbit around its companions. It is so faint that it was not discovered until 1915, when the Scottish astronomer Robert Innes identified it from the Union Observatory in Johannesburg. And because its orbit brings it fractionally closer to Earth than the other 2 stars, Proxima Centauri holds the title of the closest individual star to our Sun, 4.24 light-years. The other 2 components of the system sit a little farther out, at approximately 4.37 light-years. This would be interesting enough on its own, a triple star system sitting on our cosmic doorstep. But in 2016, the story became something larger. The European Southern Observatory announced the discovery of Proxima Centauri, orbiting within the habitable zone of the nearest star to Earth. The habitable zone is the region around a star where temperatures could theoretically allow liquid water to exist on a planet's surface. It is not a guarantee of habitability. It is a necessary condition, not a sufficient one. But for the public imagination, those details evaporated. The headline wrote itself. There is an Earth-sized planet in the habitable zone of the nearest star. It was as if the universe had placed a signpost at the edge of the solar system, pointing outward and saying, "This way to the next world." Since that discovery, more has been learned. Proxima Centauri b has a minimum mass of roughly 1.05 Earth masses. It orbits its star every 11.2 days at a distance of about 7.25 million kilometers, far closer to its star than Mercury is to the Sun. But because Proxima Centauri is a dim red dwarf with only about 1/6% of the Sun's luminosity, that tight orbit places the planet within the conservative habitable zone. There are complications. The planet is likely tidally locked, meaning one hemisphere permanently faces its star while the other faces the void. Proxima Centauri is an active star, producing intense flares and extreme ultraviolet radiation that could strip away an unprotected atmosphere. NASA models suggest that an Earth-like atmosphere at Proxima b's orbit could be eroded at rates up to 10,000 times faster than Earth loses its own atmosphere. Whether the planet retains any atmosphere at all, let alone one capable of supporting surface water or life, remains entirely unknown. But none of that dimmed the excitement. Because the real power of Proxima Centauri b was never about what was there, it was about where it was, 4.24 light-years, the nearest possible destination outside the solar system, the first place you would go if you could go anywhere among the stars. And that is where the trouble begins. Because 4.24 light-years is not a number the human brain can process honestly, let us try to make it real. A light-year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second. In 1 year, it covers roughly 9.46 trillion kilometers. Multiply that by 4.24 and you get the distance to Proxima Centauri, approximately 40.1 trillion kilometers. 40 trillion. Written out, that number has 13 digits. It is a distance so large that every unit of measurement humans use in daily life collapses under its weight. Let us try kilometers first. 40 trillion kilometers. The circumference of the Earth is about 40,000 kilometers. To cover the distance to Proxima Centauri, you would need to circle the Earth roughly 1 billion times. Not a million, a billion. 1,000 million trips around the equator, laid end to end, and you would arrive at the nearest star. Now try it with the Earth to Sun distance. The mean distance from Earth to the Sun, 1 astronomical unit, is about 150 million kilometers. The distance to Proxima Centauri is approximately 268,000 astronomical units. That means if you shrank the solar system down to a scale where the Earth and Sun were 1 inch apart, Proxima Centauri would be about 4.2 miles away. That sounds manageable, until you remember that in this same model, Jupiter would be 5 inches from the Sun, Saturn would be 9.5 inches. Neptune, the outermost major planet, would be about 2.5 feet away. The entire known solar system, everything humanity has ever visited or photographed or landed a probe on, fits within a few feet. And then there are 4.2 miles of nothing, empty, cold, dark. That is the gap. Now, Let us use the object that makes this most vivid. Voyager 1. Voyager 1 launched on September 5, 1977. It visited Jupiter in 1979 and Saturn in 1980. After its encounter with Saturn, it was flung outward on a trajectory that carried it away from the plane of the planets, heading toward interstellar space at a speed of approximately 17 kilometers per second. 61,198 kilometers per hour, roughly 38,000 miles per hour. It has never slowed down, it has never stopped. For nearly 50 years, it has been flying in a straight line away from Earth at that speed without interruption. As of early 2026, Voyager 1 is approximately 25.3 billion kilometers from Earth. By November of this year, it is projected to reach a distance of 25.9 billion kilometers, which is the distance light travels in a single day. One light day. After nearly half a century of flight at 38,000 miles per hour, the fastest object humanity has ever sent outward will finally be one day's worth of light travel from home. One light day. Proxima Centauri is 4.24 light-years away. A light-year contains 365.25 light days. 4.24 light-years contains roughly 1,549 light days. Voyager 1, after 50 years, has traveled one light day. It would need to travel for approximately 73,000 more years to reach Proxima Centauri. 73,000 years. That is not a number that belongs in a conversation about travel. That is a number that belongs in geology. 73,000 years ago, the Toba supervolcano erupted in what is now Sumatra. Modern human civilization, all of recorded history, every empire, every invention, and every war fit inside the last 10,000 years. Voyager 1 would need 7 times that span of time to drift to the nearest star, and Voyager 1 is fast. It is the fastest outbound object humanity has ever built. The New Horizons probe, which flew past Pluto in 2015, launched faster than Voyager, but has since slowed due to the Sun's gravity and is now traveling at roughly 14 kilometers per second. At that speed, the journey to Proxima Centauri would take closer to 90,000 years. The Juno spacecraft, which orbited Jupiter, reached speeds of over 70 kilometers per second during its orbital insertion burn. But that speed was relative to Jupiter and not sustainable over interplanetary distances. These numbers are not estimates buried in obscure papers. They are the straightforward mathematical consequences of dividing the distance by the speed, and they all land in the same territory. Tens of thousands of years, hundreds of centuries. But we should not stop at spacecraft. Let us try other speeds to see if anything helps. The Parker Solar Probe, launched in 2018, has achieved the fastest speed of any human-made object relative to the Sun. During its close perihelion passes, it has reached speeds of approximately 195 kilometers per second. That is absurdly fast by human standards. Fast enough to cross the entire United States in about 25 seconds. At that speed, which no interstellar spacecraft could sustain because the Parker Solar Probe achieves it only by falling toward the Sun, the trip to Proxima Centauri would take roughly 6,700 years. 6,700 years, when the first major cities were being built in Mesopotamia, when writing was being invented, when the wheel was new. A spacecraft launched at the fastest speed any human object has ever achieved and sustained somehow across the entire journey, would arrive at Alpha Centauri around the time those first cities crumbled into dust and 100 generations had lived and died on Earth without ever knowing the mission had launched. The International Space Station orbits the Earth at roughly 7.7 kilometers per second. At that speed, the journey would take over 165,000 years. That is further back than the earliest evidence of anatomically modern humans leaving Africa. Every number tells the same story. It does not matter which speed you use. It does not matter which vehicle you imagine. As long as you are using anything humanity has actually built and flown, the travel time to the nearest star is measured in millennia at best, and in geological epochs at worst. And this is where the illusion begins to crack. Because when someone says Alpha Centauri is the nearest star system, what your brain hears is nearby. It is accessible. It's the first step. The phrase nearest star borrows the emotional connotation of nearness from everyday life, where the nearest grocery store is 10 minutes away and the nearest hospital is a short drive. But in interstellar terms, nearest simply means the least horrifying number in a list of numbers that are all horrifying. The second nearest independent star system, Barnard's star, is about 6 light-years away. Sirius is about 8.6. Tau Ceti is roughly 12. Against that list, 4.24 light-years does look small. But that smallness is an artifact of comparison, not a fact about reachability. The difference between 4 light-years and 12 light-years is the difference between profoundly impossible and slightly more profoundly impossible. Neither one is close to anything a human being could cross with any technology that currently exists. There is a deeper problem with the word nearest, and it has to do with how human brains process scale. Psychologists have known for decades that the human mind is not built to comprehend very large or very small numbers intuitively. We can handle quantities of up to about a few thousand with genuine understanding. Beyond that, numbers become abstractions. They lose weight. 1,000,000, 1,000,000,000, 1,000,000,000,000. People know intellectually that 1,000,000,000,000 is 1,000 times larger than 1,000,000,000, but they do not feel it. The numbers flatten. They become emotionally equivalent. This is exactly what happens with interstellar distances. When someone hears 40 trillion kilometers, the brain registers the word trillion and files it alongside every other trillion it has heard. National debt, grains of sand on a beach, cells in the human body. The number becomes just another large thing. It loses its specific, physical, crushing meaning. And when that specific meaning is lost, the idea of traveling to Alpha Centauri stops feeling impossible and starts feeling merely difficult. Difficult is something humans are good at overcoming. We went to the moon. We built the internet. We split the atom. Surely, given enough time, we will figure out how to cross a few light years. That reasoning is seductive. It feels correct. And it is one of the most dangerous errors a person can make when thinking about interstellar space, because it confuses an engineering challenge with a fundamental constraint. Some problems are hard because we have not yet built the right tool. Those problems yield to effort, ingenuity, and time. Other problems are hard because the universe itself sets limits that do not care about ingenuity. The speed of light is one such limit. The energy required to accelerate mass is another. The interstellar medium is another. And the distance to Alpha Centauri sits squarely on the wrong side of that line, not as a puzzle waiting for a clever solution, but as a physical reality that resists every approach humanity has so far imagined. We have not yet discussed those approaches. We have not yet talked about nuclear propulsion, or light sails, or antimatter engines, or fusion drives, or any of the concepts that populate the optimistic end of the conversation. We will. And what we will find is that even the most ambitious of them, even the ones that are not science fiction, even the ones backed by real physics and real funding, do not make this problem simple. They do not turn Alpha Centauri into a destination in any normal human sense of the word. They turn it, at best, into a target for a microscopic robotic chip traveling at a fifth of light, speed of light, with no ability to slow down when it arrives. That is the honest picture. That is what nearest actually means. Not close, not reachable, not a stepping stone to the galaxy. Nearest means the first and most gentle demonstration that the stars are not where we think they are. They are not across a gulf that human ambition can bridge in the next century or two. They are across an abyss so vast that even naming it the shortest possible crossing does not make it crossable. The question that follows from this is the one every engineer and physicist who has ever thought seriously about interstellar travel has asked. If the distance is this enormous, can we at least go faster? Can we build something, anything, that moves fast enough to turn 73,000 years into something a human civilization could survive? The answer is more complicated and more heartbreaking than most people realize, because the problem is not just speed. Speed is only the door to a hallway of other problems, each one worse than the last. And behind each of those problems, standing quiet and patient, is the same number, 4.37 light-years. The nearest star, the shortest crossing, the smallest version of a problem so large that even solving the smallest version might be beyond anything our species can do. That is the question we need to answer now. The moment you accept that the distance to Alpha Centauri is real, that it is not a number waiting to be shrunk by cleverness, but a physical fact, measured in trillions of kilometers of vacuum, your mind does something very human. It pivots. It says, fine, the distance is enormous, but can we not simply go faster? This is the instinct that has driven every serious interstellar propulsion study since the 1950s. It is a good instinct. It is also the instinct that runs face first into the hardest wall in physics. To understand why, we need to talk about what speed actually costs. Not in the abstract, not in metaphor, in energy. Because energy is the currency of motion, and interstellar motion has a price tag that makes every other engineering project in human history look like pocket change. Start with the most basic version of the question. We want to send something to Alpha Centauri. Let us not be greedy. Let us not demand a crude mission. Let us start with a probe, a modest one, say 1,000 kilograms, roughly the mass of a small car. We want this probe to arrive within a human lifetime, call it 50 years. To travel 4.37 light-years in 50 years, the probe needs to move at roughly 8.7% of the speed of light, about 26,000 kilometers per second. That is the starting requirement. Anything slower, and you are back to centuries. Anything faster, and the energy demands become even more extreme. So let us treat 8 to 10% of light speed as the minimum threshold for a meaningful interstellar mission, one that could return data to the people who launched it. Now, how do you get a 1,000 kilogram object moving at 10% of the speed of light? The kinetic energy of a moving object is 1/2 times its mass times its velocity squared. At 10% of light speed, roughly 30,000 kilometers per second, the kinetic energy of a 1,000 kilogram probe is approximately 450 quadrillion joules. 450 petajoules. To put that in perspective, the atomic bomb dropped on Hiroshima released approximately 63 terajoules of energy. You would need the energy equivalent of roughly 7,000 Hiroshima bombs just to accelerate a single small car-sized probe to the minimum speed required for a 50-year crossing. And that calculation assumes perfect efficiency. Every joule of energy produced goes directly into accelerating the spacecraft, with nothing lost to heat, exhaust, structural inefficiency, or any of the 1,000 other places energy disappears in real engineering. In practice, the energy required would be many times higher, that is for a 1,000 kilogram probe. Now imagine a crewed vessel. A spacecraft capable of keeping human beings alive for decades would need to mass at a minimum of tens of thousands of tons, and more realistically, hundreds of thousands of tons, when you include the hull, the life support systems, the radiation shielding, the food production capacity, the fuel, and the structural support required to survive the journey. Scale the energy calculation up by a factor of 100,000, and you are no longer talking about bombs. You are talking about the total energy output of entire nations sustained over years, poured into a single object to make it move fast enough. This is the tyranny, not of distance alone, but of the rocket equation, the fundamental mathematical relationship between the speed you want to achieve, the speed at which your exhaust leaves your engine, and the ratio of fuel to payload you need to carry. The rocket equation is merciless. It is exponential. If you want to go twice as fast, you do not need twice as much fuel. You need enormously more. The fuel itself has mass, which requires more fuel to accelerate, which adds more mass, which requires more fuel. The curve bends upward without pity, and it breaks every propulsion system humanity has ever built, long before you reach the speeds required for interstellar travel. Let us walk through the options, one by one, starting with the ones we actually know how to build. Chemical rockets are the backbone of every space mission in human history. Every Saturn V, every space shuttle, every Falcon 9, every Soyuz, all of them run on the same basic principle. You carry a fuel and an oxidizer. You burn them together in a combustion chamber. The hot exhaust shoots out the back. The spacecraft moves forward. It works. It has taken us to the moon, to every planet in the solar system, to the heliopause and slightly beyond. It is also completely useless for interstellar travel. The problem is a quantity called specific impulse, which is a measure of how efficiently a rocket engine converts fuel into thrust. Chemical rockets have specific impulses measured in the hundreds of seconds. The most efficient chemical rockets ever built, burning liquid hydrogen and liquid oxygen, achieve a specific impulse of roughly 450 seconds. To reach even 1% of the speed of light using a chemical rocket, the mass ratio, the ratio of the fully fueled spacecraft to the empty spacecraft, would need to be so absurdly large that the fuel would outweigh the payload by a factor that has more digits than a phone number. You could not build the fuel tank. You could not launch it. The entire concept folds under its own arithmetic before you ever leave the drawing board. Chemical propulsion gets humanity to the moon in 3 days and to Mars in roughly 7 months. It does not get humanity to Alpha Centauri in any amount of time that has meaning. The next step up is nuclear propulsion, and this is where the conversation starts to feel like it might be going somewhere. Nuclear reactions release roughly 1,000,000 times more energy per unit of mass than chemical reactions. That is not a metaphor. The energy density of nuclear fuel is literally 6 to 7 orders of magnitude greater than the energy density of hydrogen and oxygen combustion. This is why nuclear propulsion has been studied seriously for interstellar applications since the 1950s. There are 2 main categories. Nuclear thermal propulsion works by using a fission reactor to heat a propellant, typically hydrogen, to extremely high temperatures, and then expelling it through a nozzle. The specific impulse roughly doubles compared to chemical rockets, reaching 800 to 900 seconds. This is a real improvement. It means you can carry less fuel for the same amount of thrust. NASA tested nuclear thermal engines during the NERVA program in the 1960s and 70s, and the concept works. Prototypes were built. They fired. The physics is demonstrated. But doubled specific impulse does not solve the interstellar problem, not even close. A nuclear thermal rocket could make a Mars transit significantly faster and more efficient. It could enable ambitious outer solar system missions. It cannot, under any realistic mass budget, propel a spacecraft to the percentages of light speed required to reach Alpha Centauri within a human lifetime. The travel times remain in the tens of thousands of years. You have moved from geological time to merely archaeological time. The improvement is real, but the destination is still unreachable. Nuclear electric propulsion takes a different approach. Instead of heating propellant directly, a nuclear reactor generates electricity which powers an ion drive or similar high-efficiency thruster. Ion drives have extraordinarily high specific impulse, often 3,000 seconds or more, meaning they are incredibly fuel efficient. The problem is thrust. Ion drives produce tiny amounts of force. They accelerate slowly. Over months and years, they can build up impressive velocities for interplanetary missions, but the sustained acceleration required to reach interstellar speeds would demand reactors of such enormous power output, running for such extended periods, that the engineering challenges become effectively insurmountable. You would need a reactor that operates flawlessly for decades, producing megawatts to gigawatts of power without interruption aboard a spacecraft that has no access to maintenance or replacement parts. No such reactor has ever been built. None is under construction. Then there is the most dramatic nuclear concept of all: Project Orion. In 1958, the physicist Ted Taylor and the mathematician Freeman Dyson began work on a spacecraft propulsion system so audacious it sounds like parody. The idea was to detonate nuclear bombs behind a massive pusher plate attached to the spacecraft. Each explosion would vaporize a portion of a propellant disk and slam plasma into the plate, pushing the ship forward. By detonating bombs in rapid sequence, the spacecraft could theoretically achieve velocities of several percent of light speed. This is not science fiction. The physics works. Detailed engineering studies were conducted. Small-scale tests using conventional explosives were performed and confirmed the basic principle. The design called for a spacecraft the size of a city block, carrying thousands of nuclear charges, accelerated by a series of controlled nuclear detonations occurring every few seconds. The numbers were real. A full-scale Orion vehicle, in its most ambitious configuration, could theoretically reach 3 to 5% of light speed. At 3% of light speed, the trip to Alpha Centauri would take roughly 140 years. At 5%, roughly 90 years. Those are still multi-generational timeframes, but they represent the first moment in the history of propulsion concepts where the number dropped below 200 years. Project Orion was killed by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. It was also killed by the obvious political and environmental objections to launching a spacecraft by detonating nuclear weapons in the atmosphere during the boost phase. And it was killed by a problem that haunts every serious interstellar concept. Even if you build it, even if you accept the political impossibility and the environmental cost, you still face a journey that lasts longer than any nation, any institution, any social structure in human history has ever survived without fundamental transformation. 140 years is not a mission duration. It is a demand that a functioning civilization maintain interest, funding, institutional memory, and technical competence across roughly 7 generations for a project whose data will be received by people who were not alive when it launched. Orion demonstrated something important. Not that interstellar travel is possible, but that even when you throw the most powerful energy source available at the problem, the answer you get back is still a century minimum. And that is the optimistic scenario. Using a propulsion method that was never built, is currently banned by an international treaty, and would require a commitment of resources and political will that has no precedent in human history. Move beyond fission and you reach fusion, the same process that powers the sun. Fusing light atomic nuclei, typically isotopes of hydrogen, into heavier nuclei releases energy far more efficiently than fission. A fusion-powered spacecraft could theoretically achieve specific impulses in the tens of thousands of seconds, potentially hundreds of thousands, and could in principle reach 5 to 15% of light speed, depending on the design. The problem is that controlled fusion does not exist. This is not a secret. The running joke in physics is that commercial fusion power is always 30 years away. After more than 70 years of research, billions of dollars of investment, and some of the most sophisticated engineering on Earth, no fusion reactor has ever produced sustained net energy. The ITER project in southern France, the largest fusion experiment in the world, announced a revised baseline in 2024 that pushed first plasma into the early to mid-2030s. And even if it works perfectly, it will be a proof of concept, not a power plant. The distance between a proof-of-concept fusion reactor on Earth and a functioning fusion engine inside a spacecraft capable of sustained acceleration to 10% of light speed is so vast that it makes the distance to Alpha Centauri look modest. This does not mean fusion propulsion is impossible. It means it is undemonstrated. And undemonstrated is a word that matters enormously when people talk about interstellar travel, because the entire conversation is saturated with concepts that are theoretically valid but have never been built, never been tested, and in many cases have no funded development path. The gap between a physics concept and a functioning spacecraft engine is not a detail. It is the entire problem. Antimatter propulsion sits at the far end of this spectrum. When matter meets antimatter, both are annihilated and converted entirely into energy. The efficiency is total. 1 gram of antimatter reacting with 1 gram of matter releases approximately 180 trillion joules of energy, enough to rival the yield of a significant nuclear weapon. As a fuel, antimatter is the most energy-dense substance known to physics. In theory, an antimatter-powered spacecraft could reach significant fractions of light speed with a manageable fuel-to-payload ratio. In practice, antimatter is a fantasy propellant. The total amount of antimatter ever produced by all the particle accelerators on Earth combined is measured in nanograms, not grams, not milligrams, nanograms, billionths of a gram. The cost of producing antimatter at current rates has been estimated at roughly $62.5 trillion per gram. The infrastructure required to produce, contain, and store macroscopic quantities of antimatter does not exist in any form. Containment is itself a fundamental problem, because antimatter annihilates on contact with any ordinary matter, requiring magnetic confinement in a perfect vacuum, a technology that currently works for individual atoms held for minutes to hours, not for grams of fuel stored for years. Antimatter propulsion is not a technology waiting to be developed. It is a concept separated from reality by multiple independent breakthroughs in particle physics, manufacturing, containment engineering, and economics, none of which are on any current development timeline. To call it speculative would be generous. To build a mission plan around it would be irresponsible. This brings us to the concept that currently dominates serious public discussion of reaching Alpha Centauri. Breakthrough starshot. In 2016, the investor Yuri Milner, the physicist Stephen Hawking, and Mark Zuckerberg announced a $100 million research program to investigate the feasibility of sending gram-scale spacecraft to Alpha Centauri within a generation. The core idea is elegant. You do not try to carry your fuel with you. Instead, you leave the engine on the ground. A massive array of ground-based lasers with a combined output of roughly 100 gigawatts, would fire a coherent beam at a light sail attached to a tiny spacecraft, a chip-sized probe weighing perhaps a few grams. The pressure of the photons hitting the sail would accelerate the probe to approximately 20% of light speed within minutes. At that speed, the crossing to Alpha Centauri would take roughly 20 years. Data could be transmitted back using the same sail as a communications antenna, arriving about 4 years later. Total time from launch to data return, roughly 24 years. 24 years. That is a number that sounds like a mission. That sounds like something a person could wait for. It sounds like progress, and in many ways, it is progress. Breakthrough Starshot represents the most serious, most well-funded, and most physically grounded attempt to turn the idea of interstellar travel into something resembling a real engineering program. The physics of laser propulsion works. The concept of a light sail is not new. The team has attracted serious scientists and engineers from institutions around the world. In 2025, researchers from Brown University and TU Delft published work on an AI-optimized light sail only 200 nanometers thick, with billions of nanoscale holes designed to reduce mass while maintaining reflectivity. The technology is being developed. It is real work, but the gap between real work and a functioning interstellar mission is enormous, and the honest assessment of Breakthrough Starshot requires listing the unsolved problems. First, the laser array. 100 gigawatts of coherent, phase-locked laser power focused on a sail the size of a bedsheet from a distance that increases to millions of kilometers in minutes. The largest laser facility on Earth, the National Ignition Facility, produces roughly 500 terawatts of power, but only for a few billionths of a second. Starshot requires a sustained output of 100 gigawatts for roughly 10 minutes. No such laser array exists. No funded program to build one is underway. The infrastructure required would be among the largest and most expensive ever constructed, comparable in power output to the entire electrical grid of a mid-sized nation concentrated into a single directed beam. Second, beam stability. The laser must track and maintain focus on a sail that is centimeters across while it accelerates to 20% of light speed. At those velocities, the sail is moving away from the laser at increasingly relativistic speeds, and any wobble, any misalignment, any atmospheric disturbance would deflect the beam and lose the sail. Adaptive optics and phase locking across a kilometer-scale laser array in real time is a problem that has not been solved at this scale. Third, survival. At 20% of light speed, the spacecraft is moving at roughly 60,000 kilometers per second. At that velocity, every grain of interstellar dust becomes a hypervelocity projectile. A particle of dust weighing less than a millionth of a gram, striking the probe at 20% of light speed, delivers energy comparable to a small explosive charge. The interstellar medium between here and Alpha Centauri is not perfectly empty. It contains roughly 1 hydrogen atom per cubic centimeter and sparse but non-zero quantities of dust. Over a journey of 4.37 light-years, the cumulative impact of dust and gas on a gram-scale probe at relativistic speed is a problem that has been studied but not fully solved. A 2016 study by Team Huang and colleagues suggested the damage might be manageable, but acknowledged significant uncertainties. Fourth, and perhaps most fundamentally, the probe cannot slow down. A gram-scale chip accelerated by a ground-based laser has no onboard propulsion. It flies past the Alpha Centauri system at 20% of light speed. The entire encounter lasts hours. During that time, the probe's cameras and sensors must collect data on the star system, including any planets, and transmit it back to Earth using a laser communication link powered by a light sail 4 million times further from the receiver than any deep space communication link ever operated. Breakthrough Starshot, even in its most optimistic scenario, does not deliver a spacecraft to Alpha Centauri. It delivers a chip through Alpha Centauri. A flyby at 60,000 kilometers per second, with no ability to orbit, no ability to linger, no ability to examine anything in detail, and communication challenges that push the limits of information theory. It is not a mission in the sense that Voyager was a mission. It is a glimpse. A single fleeting photograph taken at impossible speed and sent home across a void so wide that the return signal would require the most sensitive receiver ever conceived. And it may be the best we can do. In February 2026, a separate team proposed an alternative concept using relativistic electron beams instead of lasers to push a larger probe, roughly 1,000 kilograms, to 10% of light speed. The idea involves a statite, a structure held in a fixed position by balancing solar radiation pressure against gravity, which would fire a focused beam of electrons at the departing spacecraft over a sustained period of weeks or months. The longer push would allow a much heavier probe to be accelerated, producing a mission more comparable in capability to Voyager than to a silicon chip. The authors of the study were explicit that the concept is not ready to fly. Beam stability in the real solar magnetic environment is poorly understood. The interaction between the beam and the return current flowing through the surrounding plasma has not been validated. High-fidelity simulations and space-based experiments would be required before anyone could confirm whether such a beam stays on target across hundreds of astronomical units. The concept is promising on paper. It is theoretical in practice, and even if it works, the result is a 40-year travel time for a probe that still faces every shielding and reliability challenge described above. There is a problem we have not yet confronted directly, and it may be the cruelest one of all. Everything discussed so far has been about getting up to speed, about acceleration, about the energy and infrastructure required to push something fast enough that the travel time drops from millennia to decades. But reaching Alpha Centauri is not the same as arriving at Alpha Centauri. And arriving, in any meaningful sense, means slowing down. This is the deceleration problem. And it is where the rocket equation turns from merely tyrannical to genuinely sadistic. Consider a spacecraft that has been accelerated to 10% of light speed for a 50-year crossing. It is now approaching the Alpha Centauri system at 30,000 kilometers per second. At that velocity, the spacecraft would cross the entire diameter of our solar system, from the Sun to Neptune's orbit, in roughly 42 hours. The Alpha Centauri system, with its 3 stars and their associated planets, would be traversed in a comparable window. The spacecraft's instruments would have hours, perhaps a day or 2 at most, to observe anything before the system is behind it and shrinking into the void. If the mission's goal is anything more than a flyby, if we want to orbit a planet, deploy instruments, take sustained measurements, study Proxima Centauri b in detail, or, in the most ambitious scenario, land something on its surface, the spacecraft must decelerate. It must shed all of that velocity. Every kilometer per second that was so painfully gained during the boost phase must now be painfully lost before arrival. And deceleration, in the vacuum of space, costs exactly as much energy as acceleration. There is no air to create drag, there is no friction, there is no brake. The only way to slow down is to point your engine forward and fire it, expending fuel at the same rate and for the same duration as the original acceleration burn, but in reverse. This means the fuel budget roughly doubles, but it is worse than doubling. because the rocket equation is exponential, not linear. The fuel required for deceleration must itself be accelerated during the boost phase. You are not just carrying fuel to slow down, you are carrying fuel to accelerate, and you will need to slow down. And you are carrying fuel to accelerate that fuel. The mass ratio compounds at every level. For a spacecraft using onboard propulsion, this transforms the already staggering fuel requirements into something nearly incomprehensible. If reaching 10% of light speed with a given engine requires a mass ratio of, say, 20:1, meaning 20 kilograms of fuel for every kilogram of payload, then reaching 10% of light speed and then decelerating back to rest requires a mass ratio of roughly 400:1. 400 kilograms of fuel for every kilogram of spacecraft that arrives at rest in the Alpha Centauri system. For a 1,000 kilogram probe, that means 400,000 kilograms of fuel. 400 tons, launched from Earth, accelerated to relativistic speed, and then burned in reverse upon arrival. The engineering challenges of containing, managing, and expelling 400 tons of propellant aboard an interstellar spacecraft over the course of decades are beyond anything in current aerospace practice. Some mission concepts attempt to sidestep the deceleration problem by using the destination itself. A light sail, for example, could theoretically use the radiation pressure of Alpha Centauri's stars to decelerate, flipping the sail to catch starlight as a braking force. This is called a photogravitational assist, and researchers have published studies suggesting it could work in principle, but the maneuver requires extraordinary precision. The sail must be oriented exactly right, at exactly the right distance, traveling at exactly the right speed, through a gravitational field shaped by 3 separate stars. The margin for error is essentially zero, and the deceleration is slow, meaning the spacecraft must survive an extended period of close approach to an alien star, enduring radiation and thermal loads that add yet more engineering constraints. A magnetic sail, which generates drag against the charged particles in the stellar wind of the destination star, has also been proposed as a deceleration mechanism. The concept has theoretical merit, but the engineering has never been demonstrated, even in laboratory conditions, and the deceleration rates achievable depend heavily on the density and speed of the stellar wind at Alpha Centauri, which are not precisely known. The deceleration problem is why Breakthrough Starshot is designed as a flyby. The designers understood from the beginning that slowing down a gram-scale probe traveling at 20% of light speed is effectively impossible with any onboard system. The probe carries no engine. It has no fuel. It screams through the Alpha Centauri system at 60,000 kilometers per second and keeps going, forever. The mission accepts this limitation because the alternative, carrying enough fuel or equipment to stop, would make the entire concept unworkable. This is a concession so enormous that it deserves to be stated plainly. The most credible interstellar mission concept currently under development has already surrendered the possibility of arrival. It can visit, in the loosest possible sense of the word, but it cannot stay. It cannot orbit, it cannot land, it cannot do anything that a planetary scientist would recognize as exploration. It is a momentary glance at a system we cannot reach, taken at a speed so great that the glance lasts less than a day. That is not failure, it is a remarkable achievement, if it ever happens. But it illuminates the depth of the problem in a way that no amount of discussion about acceleration can. Because the real question was never just, how do we get there? The real question was always, how do we stop? And so far, the best answer anyone has is that we do not. Notice the pattern. Every propulsion concept that produces interstellar relevant speeds is either unbuilt, underfunded, banned, physically undemonstrated, or limited to payloads so small they can barely carry a camera. The concepts that are buildable chemical and nuclear thermal rockets produce travel times measured in millennia. The concepts that are fast enough, antimatter, fusion, and relativistic beams, exist only as equations and small-scale experiments. And the one concept that sits closest to the boundary between theoretical and real, breakthrough starshot, delivers a gram-scale flyby with no ability to stop. There is a phrase used in aerospace engineering that captures this perfectly: the tyranny of the rocket equation. It was coined by Donald Pettit, a NASA astronaut and engineer, to describe the exponential relationship between velocity and fuel mass that makes high-speed spaceflight so punishing. But for interstellar travel, the tyranny is worse than the equation alone. It is the tyranny of compounding impossibilities. You need speed, which demands energy, which demands fuel or infrastructure, which demands mass or scale, which demands more energy, which demands more fuel. Each solution to one problem creates a new version of the same problem at a higher level. And propulsion is only the first barrier, even if you solved it. Even if someone built a working fusion drive or a 100-gigawatt laser array or discovered a way to produce antimatter in bulk. Even if the speed problem were eliminated and you could accelerate a spacecraft to 10% of light speed with a reasonable fuel budget and a proven engine, you would still face the wall behind the wall. The problems that do not care how fast you are going are about what happens during the journey and what happens when you arrive. Shielding, survival, reliability, energy for systems that must operate for decades without failure, communication across distances where a radio signal takes years to arrive. The structural integrity of a vessel bombarded by the interstellar medium at speeds where every hydrogen atom becomes a bullet. Propulsion is the lock on the door. But behind the door is a corridor of locked doors, each one harder to open than the last. And at the end of the corridor, 4.37 light-years away, sits a star system that does not care whether you arrive or not. That corridor is what we need to walk through now. There is a seductive idea embedded in almost every conversation about interstellar travel. It goes like this: the hard part is getting up to speed. Once you solve propulsion, the rest is engineering. Better materials, better computers, better life support. Details. The kind of problems that smart people solve once the funding arrives. This idea is wrong, and the way it is wrong reveals something important about how people think about space. We are conditioned by decades of spaceflight history to believe that the primary obstacle to reaching a destination is the rocket. Build a big enough rocket and you can go anywhere. That was true for the Moon. It was roughly true for Mars. It is catastrophically false for Alpha Centauri, because the distance to another star system does not just create a propulsion problem. It creates an entire ecosystem of problems, each one independently severe, each one interacting with the others in ways that multiply rather than add. Solving propulsion without solving these other problems is like building a bridge with no road on either end. The bridge might be magnificent. It still does not get you where you need to go. Let us walk through the walls that stand behind the wall of propulsion, one at a time. And let us be precise about why each one is not merely difficult, but potentially civilization scale in its demands. The first wall is energy, and not the energy of acceleration. We have already seen what that looks like. This is the energy of survival. A spacecraft crossing the void between here and Alpha Centauri, regardless of its speed, needs power. Not just during the boost phase, not just during the flyby, continuously, for the entire duration of the journey. Consider what a functioning interstellar probe requires. It needs to maintain its onboard computers, which must operate for decades without external input. It needs to power its communication system, which must be capable of transmitting data across light years to a receiver on or near Earth. It needs to run its attitude control systems, the mechanisms that keep its antenna pointed in the right direction, its cameras aimed at the target, and its trajectory stable. It needs to regulate its thermal environment, because the space is not at a uniform temperature. Depending on orientation and distance from any star, components can be simultaneously baking on one side and freezing on the other. And if the probe carries any instruments that require active cooling, as many infrared sensors do, it needs to power those systems as well. For a crewed vessel, the energy demands are orders of magnitude greater. Life support alone, providing breathable air, clean water, food production, waste processing, thermal regulation, and lighting for a human crew, requires sustained power output measured in hundreds of kilowatts to megawatts, depending on crew size. Add artificial gravity if rotation-based systems are used. Add medical equipment. Add the computational overhead of managing a closed ecosystem for decades. The total continuous power budget for a crewed interstellar vessel could easily reach tens of megawatts, and that power must be available every second of every day for the entire crossing. Where does this energy come from? Solar power is eliminated almost immediately. The intensity of sunlight drops off with the square of the distance from the Sun. By the time a spacecraft passes the orbit of Jupiter, roughly 5 astronomical units out, solar flux has dropped to about 4% of its value at Earth's orbit. By the time it passes Neptune, at 30 astronomical units, solar flux is roughly 1/9 of 1% of what it is at Earth. By the time it enters interstellar space, the Sun is an unremarkable point of light among millions. Solar panels become decorative. Nuclear fission is the current best option for long-duration deep space power, and it is what powers Voyager's instruments today, in a sense. The Voyager probes use radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 into electricity. These generators are reliable and have operated for nearly 50 years, but they are also weak. Each of Voyager's 3 RTGs originally produced about 157 watts of electrical power. Combined, roughly 470 watts at launch. Today, after nearly 5 decades of radioactive decay, that output has dropped to roughly 220 watts, enough to run a few dim light bulbs. Not enough to power the communications, computation, and instrumentation that a serious interstellar probe would require, let alone a crewed vessel. Larger fission reactors could produce more power, and NASA has tested space-rated fission reactors in limited capacities. The Kilopower project demonstrated a small fission reactor producing roughly 1 kilowatt of electrical power, designed for lunar surface operations. Scaling that to the tens or hundreds of kilowatts required for an interstellar probe is conceivable. Scaling it to the megawatts required for a crewed vessel is a different engineering universe. And any fission reactor has a finite fuel supply. Uranium and plutonium do not last forever. A reactor sized for a 50-year mission would need enough fuel to sustain operations for the entire crossing, plus contingency reserves, plus shielding for the crew against the reactor's own radiation. The fuel has mass. The shielding has mass. And mass, as we have established, is the enemy of interstellar travel, because every kilogram demands energy to accelerate. Fusion power, if it worked, could theoretically solve the energy problem for a crewed vessel. A fusion reactor producing tens of megawatts from hydrogen fuel would provide both propulsion and onboard power from a fuel source that is relatively abundant and energy-dense. This is why fusion appears in so many interstellar mission concepts. It solves 2 problems at once. But, as we have seen, controlled fusion does not exist in any sustained, net energy-producing form on Earth, let alone in a compact, lightweight, maintenance-free configuration suitable for a spacecraft that must operate autonomously for half a century or more. The energy problem is not glamorous. It does not make headlines, but it is as fundamental as propulsion, and it has no clean solution. Every interstellar mission concept, robotic or crude, must answer the question of where continuous power comes from across a journey measured in decades. And the honest answer for most concepts is that the answer does not yet exist. The second wall is the one that most people have never considered, because it operates in a domain that human experience provides no intuition for, shielding against the interstellar medium. Most people imagine interstellar space as empty. It is not. The space between stars contains a thin but non-zero distribution of matter. In the local interstellar medium through which any spacecraft departing the solar system would travel, the density is approximately 1/10 of an atom per cubic centimeter, primarily hydrogen, with traces of helium and heavier elements. There are also dust grains, microscopic particles of silicates, carbon compounds, and ice scattered sparsely but persistently across the void. At the speeds we move through space today, this material is irrelevant. Voyager 1 passes through it without incident because at 17 kilometers per second, the energy of each individual hydrogen atom striking the spacecraft is negligible. The atoms bounce off or are absorbed without effect. The spacecraft does not notice. At interstellar speeds, everything changes. At 10% of light speed, roughly 30,000 kilometers per second, every hydrogen atom in the path of the spacecraft becomes a high-energy particle. The kinetic energy of a proton hitting a surface at 10% of light speed is approximately 5 mega-electron volts. That is not a gentle tap. That is comparable to the energy of alpha particles emitted by heavy radioactive elements, enough to break molecular bonds and damage any material it strikes. Each individual proton at that speed deposits enough energy to damage molecular bonds in the materials it strikes. And there is not just one proton, there are many. At a density of 1/10 of an atom per cubic centimeter, a spacecraft with a cross-section of 10 square meters traveling at 10% of light speed would intercept approximately 30 trillion hydrogen atoms per second. Each one carries roughly 5 mega-electron volts of energy. The cumulative radiation flux is staggering beyond anything encountered in near-Earth spaceflight. Researchers studying this problem have described it as equivalent to flying face-first into the beam of a particle accelerator, because at relativistic speeds, the interstellar medium effectively becomes one. This is not a theoretical concern, it is a physical certainty. The atoms are there, the speed converts them into radiation, and the consequences are twofold. First, the radiation damages the spacecraft itself. Electronics, sensors, and structural materials all are degraded by sustained proton bombardment. Radiation-hardened electronics used in current space missions are designed to withstand the much gentler radiation environment of the inner solar system, where the Earth's magnetosphere and the Sun's heliosphere provide significant shielding. In interstellar space at relativistic speeds, the radiation environment is qualitatively different and orders of magnitude more intense. Second, the neutral hydrogen component of the interstellar medium cannot be deflected by magnetic fields. Magnetic shielding, which works by bending the paths of charged particles away from the spacecraft, is effective against ionized hydrogen and cosmic rays. It is useless against neutral atoms, which carry no charge and sail straight through any magnetic field. This means that some form of material shielding is necessary. A physical barrier between the interstellar medium and the spacecraft, dense enough and thick enough to absorb the incoming stream of relativistic hydrogen. The mass of that shield is not trivial. Studies of interstellar shielding requirements suggest that a shield capable of protecting a spacecraft at 10% of light speed would need to be composed of a low atomic number material. Hydrogen-rich polymers or water ice are commonly proposed, with a thickness sufficient to attenuate the proton flux to safe levels. The required thickness depends on the speed and the acceptable dose rate, but estimates range from meters to tens of meters of solid material across the entire forward face of the spacecraft. That material has mass, potentially hundreds to thousands of tons, depending on the design. And here is where the compounding begins. More shielding mass means more total mass to accelerate. More total mass means more energy required to reach interstellar speed. More energy means more fuel, which adds more mass, which requires more shielding because the shield must also protect the additional fuel structures. Every solution to the shielding problem makes the propulsion problem worse, and every solution to the propulsion problem, if it involves greater speed, makes the shielding problem worse. The two are locked in a spiral that tightens with every iteration. Interstellar dust presents an even more dramatic hazard, not because of radiation, but because of kinetic impact. A dust grain, with a mass of 1/10 of a microgram, a particle smaller than a grain of pollen, striking a surface at 10% of light speed, releases roughly 45,000 joules of energy, comparable to detonating 10 grams of TNT against the hull. At 20% of light speed, the energy scales by the square of the velocity, quadrupling the destructive force. Over a journey of 4.37 light-years, even the sparse dust density of the local interstellar medium guarantees numerous impacts. For a gram-scale probe like those proposed by Breakthrough Starshot, a single impact from a relatively large dust grain could be mission-ending. For a larger spacecraft, the cumulative erosion of forward surfaces over years of travel is a genuine structural concern. Some proposals have suggested deploying a forward-facing shield of sacrificial material, essentially an ablative bumper that erodes over the course of the journey, absorbing dust impacts so the spacecraft behind it does not. This adds yet more mass. Others have proposed using charged particle beams or laser systems to vaporize incoming dust grains before they strike the hull. This adds complexity, energy demand, and potential points of failure to a system that must operate flawlessly for decades. The shielding problem, like the energy problem, has no clean solution at current technology levels. It is not a matter of building better armor. It is a matter of physics. Speed turns empty space into a hostile medium, and faster is not just harder on the engine, it is harder on everything. There is a dimension of the shielding problem that goes beyond materials and mass budgets. It concerns what radiation does to living tissue over time, and it draws on research that NASA has been conducting for decades in preparation for missions to Mars, missions that involve radiation exposures far milder than anything an interstellar crew would face. Galactic cosmic rays are the primary concern. These are not the relatively low-energy protons from the Sun that dominate the radiation environment near Earth. They are high-energy nuclei, some as heavy as iron, accelerated to near-light speeds by supernova remnants and other violent astrophysical processes. They carry enormous kinetic energy per particle, and when they strike biological tissue, they do not merely ionize individual atoms. They carve dense tracks of destruction through cells, shattering DNA strands in patterns that the body's repair mechanisms struggle to fix. NASA's Human Research Program has studied the effects of galactic cosmic rays using particle accelerator facilities that simulate the STAFF, deep space radiation environment. The findings are sobering. Sustained exposure to galactic cosmic rays at the flux levels expected beyond the Earth's magnetosphere significantly increases the lifetime risk of cancer. But cancer is not the only concern, and it may not even be the most serious one. Research published over the past decade has demonstrated that heavy ion radiation causes measurable degradation of the central nervous system. Animal studies using simulated galactic cosmic ray fields have shown impairment of cognitive function, including deficits in learning, memory, and decision-making, along with increased anxiety-like behavior. These effects appear at radiation doses consistent with multi-year deep space missions. The mechanism involves chronic inflammation in brain tissue and damage to the synaptic connections between neurons, damage that accumulates over time and does not fully heal. Cardiovascular damage is another documented consequence. Studies of Apollo astronauts, who spent relatively brief periods beyond the magnetosphere, found elevated rates of cardiovascular disease compared to astronauts who flew only in low Earth orbit. The sample sizes are small, and the correlations are not fully established, but the pattern is consistent with what radiation biology predicts. Sustained exposure to heavy ion radiation damages the endothelial cells that line blood vessels, accelerating atherosclerosis and increasing the risk of heart attack and stroke. For an interstellar crew exposed to this environment for decades rather than days, the cumulative biological damage would be profound even with significant shielding. No amount of material between the crew and the cosmos can reduce the radiation dose to zero. Some fraction of galactic cosmic rays, particularly the most energetic ones, will penetrate any practical shield. The residual dose, accumulated over 30, 50, or 100 years of flight, could result in a crew that arrives at its destination with severely degraded cognitive function, elevated cancer rates, compromised cardiovascular systems, and weakened immune responses. This is not speculation about exotic hazards. It is the extrapolation of measured biological effects using data from NASA's own research programs. There is also a problem that receives almost no public attention, but that mission designers consider fundamental. Navigation. Within the solar system, spacecraft navigate using a combination of three methods. Ground-based tracking, in which the Deep Space Network measures the Doppler shift and round-trip light time of signals exchanged with the spacecraft to calculate its position and velocity. Onboard star trackers, which photograph known stars and compare their positions to a catalogue to determine orientation. And, for the final approach to planets, optical navigation, in which onboard cameras image the target body and use its apparent size and position to refine the trajectory. In interstellar space, the first method fails entirely. At distances where round-trip communication takes years, ground-based tracking cannot provide real-time course corrections. The spacecraft must navigate autonomously. Star trackers remain useful for determining orientation, which is to say, which direction the spacecraft is pointing. But determining position, where the spacecraft actually is along its trajectory, becomes extraordinarily difficult. The reason is that stars are far away. From almost anywhere in the interstellar medium between the Sun and Alpha Centauri, the background star field looks nearly identical. The angular positions of distant stars change by tiny fractions of an arc-second as you move a few light-years. Measuring your own position along the trajectory by observing stars requires detecting these minuscule parallax shifts with precision that exceeds any star tracker currently in operation. Errors compound over time. A trajectory error of even a small fraction of a degree, introduced at the moment of launch and never corrected, would grow over 4 light-years into a missed distance of billions of kilometers. For a flyby mission, this might mean passing through the Alpha Centauri system at such a distance that no useful data can be collected. For a mission intending to enter orbit around Proxima Centauri b, the required trajectory accuracy is measured in fractions of an arc-second, sustained over decades. with no ground-based correction available. This is a solvable problem in principle. Advanced onboard sensors, combined with autonomous navigation algorithms, could potentially maintain the required accuracy. But it is yet another system that must function perfectly, for decades, without human intervention or repair. Another entry in the growing list of things that must work flawlessly across timescales that exceed the operational lifetime of any autonomous system ever built. The third wall is survival, not of the spacecraft, but of the mission itself over time. This breaks into two very different categories depending on whether the vessel carries humans. For a robotic probe, survival means reliability. No machine humanity has ever built has operated continuously for the time scales involved in an interstellar crossing. Voyager 1, the longest operating deep space mission, is approaching 50 years. It is also failing. Its power output has declined to the point where instruments are being shut off one by one. Its thruster fuel is running low. Its flight data system experienced a critical malfunction in 2023 that took months to diagnose and repair from Earth, a luxury that would not be available to a probe in interstellar space, where round-trip communication takes years. In late 2024, a fault protection event caused Voyager 1 to switch from its primary X-band transmitter to a backup S-band transmitter, last used in 1981. Engineers recovered the situation, but the episode illustrates a fundamental truth. Complex systems degrade, components fail. Software encounters states that were never tested, and over decades, the probability of a mission-ending failure approaches certainty unless the system is designed with redundancy levels that far exceed anything currently standard in spacecraft engineering. An interstellar probe operating for 50 years without any possibility of repair or intervention from Earth must carry redundant systems for every critical function, redundant computers, redundant communication hardware, redundant power sources, redundant attitude control. Each redundant system adds mass, demands power, and introduces additional failure modes of its own. The more redundancy you add, the heavier and more complex the spacecraft becomes, which pushes against every other constraint in the design. For a crewed mission, the survival problem transforms from an engineering challenge into a civilizational one. No human being has ever lived in a closed environment disconnected from Earth's biosphere for more than roughly a year, and even the International Space Station is not fully closed. It receives regular supply missions. Its atmosphere is partially replenished from Earth. Its water recycling system achieves roughly 90% efficiency, but still requires supplementation. A crewed interstellar vessel would need to achieve 100% closure or carry enough consumable supplies for the entire journey, a mass penalty that would dwarf every other component of the mission. The biosphere, too, experiment in the early 1990s attempted to create a sealed, self-sustaining ecosystem on Earth. With the advantage of full gravity, sunlight, and immediate access to repair teams outside the enclosure, it failed. Oxygen levels dropped. Carbon dioxide spiked. Crops underperformed. Social conflicts erupted among the crew. The ecosystem could not sustain itself without external intervention. That was on the ground, with the entire infrastructure of human civilization outside the airlock. A crewed interstellar mission would need to solve the same problem, and solve it perfectly, inside a vessel hurtling through vacuum with no external support for decades. Generation ships, the concept of vessels large enough to sustain a human population across multiple lifetimes of travel, introduce problems that leave the domain of engineering entirely. Governance, social structure, genetic diversity, cultural continuity. psychological endurance across generations born and raised inside a metal cylinder who have never seen the sky. The anthropological and sociological literature on isolated communities suggests that groups below roughly 500 individuals face significant risks of genetic bottleneck, social fragmentation, and institutional collapse over periods of even a few hundred years. Maintaining a viable human population across a journey of centuries or millennia would require careful management of reproduction, education, resource allocation, and conflict resolution by a governing structure that must itself survive intact for the duration of the journey. No human institution has ever demonstrated that kind of stability. Nations rise and fall on time scales of centuries, religious schism, languages drift. The idea that a self-contained community could maintain coherent purpose and functional governance for 1,000 years inside a spacecraft has no historical precedent and no experimental support. It is not impossible in the way that faster-than-light travel is impossible. It is impossible in the way that perfect human cooperation is impossible. Not forbidden by physics, but contrary to everything we know about ourselves, the fourth wall is communication. Even if a spacecraft reaches Alpha Centauri, it must send data home. At 4.37 light-years, a radio signal takes 4.37 years to travel back to Earth. This is a one-way delay. A round-trip exchange takes nearly 9 years. Any question asked of the spacecraft from Earth will not receive an answer until almost a decade later. The spacecraft must be fully autonomous, capable of making every decision about data collection, navigation, and system management without ground support. But the problem is worse than the delay. It is the signal strength. The power required to transmit a detectable signal increases with the square of the distance. The Deep Space Network, the most sensitive radio receiver array on Earth, can communicate with Voyager 1 at its current distance of roughly 1 light day. The signal is vanishingly faint, arriving with a power of approximately 10 to the negative 16 watts, and requires the combined effort of multiple 70-meter dish antennas to detect. Alpha Centauri is roughly 1,600 times farther away than Voyager 1's current position. The signal strength at that distance would be roughly 2.5 million times weaker, assuming the same transmitter power. To maintain any reasonable data rate across that distance, either the spacecraft must carry an enormously powerful transmitter, adding mass and power demands, or the receiving array on Earth must be scaled up to dimensions that dwarf any existing radio telescope. Breakthrough Starshot proposes to solve this by using the light sail itself as a communication reflector, bouncing a low-power laser signal back toward Earth. The data rate would be vanishingly low, perhaps a few bits per second, enough to transmit a photograph over the course of months. Not enough to stream video, not enough to transmit detailed spectroscopic data, not enough to do anything resembling the rich data return that modern planetary missions achieve. And even this minimal communication depends on the probe surviving the journey, maintaining its orientation, and transmitting successfully across a distance at which no laser communication link has ever been tested. Now, step back and look at all 4 walls together: energy, shielding, survival, communication. Each one is independently a severe constraint. Each one has no demonstrated solution at the scale required for an interstellar mission, and critically, they do not exist in isolation. They compound. More shielding mass means more energy needed for acceleration and more power needed during the journey. More energy systems mean more mass and more heat to dissipate in a vacuum, where thermal management is already a challenge. Longer mission duration means more redundancy needed, which means more mass, which means more energy, which means more shielding for the additional systems. Better communication requires more power, which requires larger energy systems, which add mass, which must be shielded, which adds mass again. This compounding is the true nature of the interstellar problem. It is not a single wall to be climbed. It is a series of walls, each one taller because you climbed the last one. The physics does not relent, the engineering does not simplify, and the numbers do not converge on a feasible design when you include all the constraints simultaneously. Some researchers have described this as the infrastructure trap. Every component of an interstellar mission, when designed in isolation, seems achievable with sufficient investment. A powerful enough engine, a thick enough shield, a reliable enough computer, a sensitive enough antenna. But when you integrate all the components into a single design, the total mass, energy, and complexity requirements escalate beyond anything that fits inside a buildable spacecraft. The individual pieces are plausible. The assembly is not. This is not pessimism. It is accounting. The same kind of accounting that engineers do for every real mission, adding up the mass budgets, the power budgets, the thermal budgets, the reliability budgets, and checking whether the numbers close. For missions to the Moon, they close. For missions to Mars, they close with difficulty and significant risk. For missions to the outer solar system, they close with decades of travel time and stripped-down instrument packages. For missions to Alpha Centauri, the numbers do not close. Not for crewed missions. Not for large robotic missions. Barely, and only with heroic assumptions. For gram-scale probes moving too fast to stop. And this is the answer that the engineering gives us when we ask the most natural question a human being can ask after hearing how far away the nearest star is. Can we not just build something better? The answer is not no. The answer is that better is not good enough. The gap between what we can build and what the crossing demands is not a gap that incremental improvement will close. It is a gap that may require fundamental breakthroughs in multiple independent fields of physics and engineering, breakthroughs that are not on any current timeline, breakthroughs that may not be possible at all within the physical laws as we understand them. The stars are not hiding behind a problem we have not tried hard enough to solve. They are hiding behind the structure of reality itself. And the nearest one, the closest, the most accessible, the one we call our neighbor, is the place where this truth becomes impossible to ignore. What that truth means for us, for the species that looked up and dreamed of crossing, is what remains to be said. There is a moment in every honest reckoning with interstellar travel where the engineering stops mattering and the real question arrives. Not can we build a faster engine, not can we develop better shielding, not can we design a reactor that lasts for 70 years without maintenance. Those are all important questions, and we have spent a long time with them. But the question that actually matters, the one that Alpha Centauri has been asking since the first astronomer measured the distance, is simpler and harder. What does it mean that the nearest star is this far away? Not what does it mean for propulsion budgets or mission architectures? What does it mean for us? For the species that evolved under these stars and told itself stories about living among them. For the civilization that built rockets and satellites and space stations and looked outward and assumed, with an almost religious confidence, that outward was a direction it could keep going forever. Alpha Centauri answers that question. And the answer is not the one most people want to hear. To understand why, we need to separate three things that are almost always blurred together in public conversation about reaching another star. Three things that sound similar, but are radically, fundamentally different in what they demand. Sending a signal, sending a probe, and sending a human being. Sending a signal to Alpha Centauri is trivially easy. We have already done it, in a sense. Every radio transmission, every television broadcast, Every radar pulse that has ever left Earth's surface has propagated outward at the speed of light in all directions. The earliest of those signals, dating from the 1920s, has already passed well beyond Alpha Centauri. They are faint, far too faint to be detected by any receiver we know how to build at that distance, but they are there. The photons are real. They made the journey. If we wanted to send a deliberate, high-power signal to Alpha Centauri, we could do it today. Point a sufficiently powerful radio transmitter or laser at the system and fire. The signal would arrive in 4 years and 4 months. The physics is straightforward. The engineering is within current capability. The Arecibo message, transmitted in 1974 toward a globular cluster roughly 25,000 light-years away, demonstrated that humanity can and does deliberately broadcast into deep space. Reaching Alpha Centauri with a targeted signal is incomparably easier than reaching a cluster on the far side of the galaxy. But a signal is not a visit. A signal carries information. It does not carry instruments. It does not carry cameras, spectrometers, or magnetometers. It does not collect data. It does not observe. It does not return anything except the knowledge that photons left here and arrived there, which is itself only confirmable if someone or something on the other end sends a response. Sending a signal to Alpha Centauri is a solved problem that tells us almost nothing about what is there. Sending a probe is the next level, and this is where the difficulty undergoes its first brutal escalation. A probe must be built, accelerated, navigated, shielded, powered, and operated across a distance that dwarfs anything in the history of spaceflight. We have covered in detail why each of those requirements pushes against the boundaries of known engineering. But let us summarize the honest state of the field. The most credible near-term concept for sending a probe to Alpha Centauri is breakthrough starshot, or something architecturally similar to it. Gram-scale chips, pushed by ground-based lasers to a significant fraction of light speed, flying past the target system and transmitting back whatever data they can collect during a fleeting encounter. This concept has real physics behind it. Real research is being conducted. Real money has been invested. If the unsolved problems, the laser array, the beam stability, the dust survival, and the communication link are eventually resolved, it is conceivable that a flyby probe could reach Alpha Centauri within the lifetime of people alive today. Conceivable, not probable, not planned, not funded, not on any national space agency's roadmap. Conceivable in the sense that no known law of physics forbids it, that the engineering challenges, while severe, do not appear to require new physics to overcome, and that a sufficiently determined and well-funded civilization could, in principle, make it happen. This is a meaningful statement. It means the door is not locked by the laws of nature, but it is also a profoundly limited statement, because the probe that might pass through that door is a chip the size of a postage stamp, carrying instruments measured in milligrams, flying past its target at 60,000 kilometers per second with no ability to slow down, orbit, land, or linger. It would collect seconds to minutes of close-range data during its transit. It would transmit that data back at a rate so slow that a single high-resolution image might take months to arrive. And it would then continue onward into the void, its mission complete, unable to return or be redirected. That is not exploration in the sense that most people imagine when they hear the phrase, reaching another star. It is a bullet with a camera, fired across the galaxy, hoping to photograph something meaningful in the fraction of a second it spends within range. It is extraordinary, it is heroic, and it is almost unimaginably less than what science fiction has taught us to expect. Now consider the third level, sending a human being. This is where the conversation leaves engineering and enters something closer to mythology. Not because it violates physics. As far as we know, no law of nature prevents a human body from traveling to Alpha Centauri. The speed of light is a limit on speed, not on distance. In principle, given enough time, a person could drift there at walking pace. The question is not whether the physics allows it. The question is whether the engineering, the energy, the biology, the psychology, the sociology, the economics, and the institutional continuity required to execute such a mission could ever plausibly be assembled by a real human civilization. We have covered the compounding constraints. The energy required to accelerate a crewed vessel to even a modest fraction of light speed exceeds the total output of nations. The shielding required to protect human bodies from the relativistic interstellar medium adds thousands of tons of mass. The life support systems required to sustain a crew for decades to centuries have never been demonstrated in any closed environment. The reliability required for systems that must operate for longer than any machine in history exceeds any demonstrated engineering practice. The communication delay renders ground support meaningless. The governance and social stability required for a generation ship have no precedent in any human society. Each of these is a separate problem. Together, they form a wall so high and so thick that no current or credibly proposed technology comes close to surmounting it. A crewed mission to Alpha Centauri is not on any space agency's development timeline. It is not in any funded research program. It is not the subject of any engineering design study that concludes with a feasible architecture. It exists exclusively in the domain of speculation, aspiration, and science fiction. This is the distinction that must be stated clearly, because public discourse almost never states it. There is a vast difference between something that is not forbidden by physics and something achievable by a civilization. Faster-than-light travel appears to be forbidden by physics. Crewed interstellar travel does not appear to be forbidden by physics, but the gap between not forbidden and achievable is oceanic. Many things are not forbidden by physics that remain permanently out of reach for practical, economic, energetic, or biological reasons. It is not forbidden by physics to disassemble Mercury and reassemble it into a ring around the Sun. It is not forbidden by physics to lower the temperature of the Earth's core by 10 degrees. These things are simply so far beyond any conceivable capability that calling them possible is technically accurate and operationally meaningless. A crewed mission to Alpha Centauri may not belong in that category forever. Breakthroughs in fusion propulsion, in materials science, in closed-loop life support, in artificial intelligence, in any of a dozen fields could change the calculation. But it belongs in that category now. And it has belonged in that category for the entire history of spaceflight. And no currently identified development path moves it out of that category within any timeline measured in decades. So, why does the dream persist? Why does every article about Alpha Centauri end with optimism? Why does the phrase, "our first interstellar destination," appear in popular science writing as though the trip were a matter of scheduling rather than a matter of reinventing civilization? Part of the answer is psychological. The human brain is spectacularly bad at accepting limits. Our entire evolutionary history is a story of overcoming barriers. Rivers, mountains, oceans, the atmosphere, the vacuum of near-Earth space, the surface of the moon. Every boundary we have ever encountered has eventually been crossed. This creates a deeply embedded cognitive pattern, a reflexive assumption that all boundaries are temporary, that given enough time, enough ingenuity, enough will, any distance can be traveled, any obstacle can be overcome. This assumption has served our species extraordinarily well on Earth and in the inner solar system. It is also completely untested against the interstellar medium. The distances and energies involved in crossing between stars are not incrementally larger than the distances and energies involved in crossing between planets. They are categorically different. The ratio between the distance to Mars at its closest approach and the distance to Alpha Centauri is roughly the same as the ratio between the width of a human hair and the length of a football field. These are not the same kind of problem at different scales. They are different kinds of problems entirely. And the intuition that worked for the first kind may not apply to the second. There is a deeper flaw in the reasoning that says we will eventually solve this because we always have. The flaw is the assumption that technological progress is unbounded, that every field of engineering improves indefinitely, that every barrier eventually falls to human ingenuity, given enough centuries of effort. History does not support this. History shows that some technologies improve rapidly, plateau, and then stop advancing in any fundamental way. The internal combustion engine improved dramatically between the 1880s and the 1960s. Since then, gains have been incremental. Efficiencies have crept up by single percentage points per decade. The fundamental thermodynamic limits of the Otto cycle and the diesel cycle impose a ceiling that no amount of engineering cleverness can breach. You cannot extract more energy from a fuel than the fuel contains, and you cannot convert heat to work with perfect efficiency. These are constraints set by the laws of thermodynamics, not by the state of the art. The same pattern appears in aviation. The speed of commercial aircraft increased rapidly from the 1930s through the 1960s, culminating in the Concorde, which cruised at over twice the speed of sound. Then it stopped. The Concorde was retired in 2003, and no commercial aircraft has flown faster. The reasons are physical and economic. Supersonic flight generates shock waves that waste energy and produce sonic booms. The fuel consumption per passenger mile at supersonic speeds is several times higher than at subsonic speeds. The physics of air resistance sets a practical ceiling on how fast it makes sense to fly through an atmosphere, and humanity reached that ceiling half a century ago. Chemical rocket performance tells the same story. The specific impulse of the most efficient chemical propellants, liquid hydrogen and liquid oxygen, was well understood by the 1960s. No fundamental improvement has been made since. The energy available from hydrogen-oxygen combustion is fixed by chemistry. You can optimize the nozzle, refine the turbopumps, and reduce structural mass, but you cannot make the reaction release more energy. The ceiling is defined by the molecular bond energies of the reactants, and we reached it decades ago. The pattern is clear. Technologies that operate close to fundamental physical limits improve rapidly early in their development, then slow, then stop. The early gains are in engineering. The final limits are physics. And the distinction between the two is precisely the distinction that matters for interstellar travel. The question is not whether we will build better rockets. We will. The question is whether better rockets, better reactors, better materials, better algorithms can close a gap that is defined not by our current level of engineering, but by the physical constants of the universe. The speed of light, the energy density of fusion, the mass-energy equivalence governs how much fuel you need to carry. These are not engineering parameters awaiting improvement. They are features of reality. People who argue that interstellar travel will eventually become routine often draw analogies to the history of ocean crossing. In the 15th century, crossing the Atlantic was a dangerous, multi-month ordeal. By the 20th century, it was a 6-hour flight. Surely, the same trajectory applies to the stars. But this analogy collapses under inspection. The Atlantic Ocean is roughly 5,000 kilometers wide. The distance to Alpha Centauri is roughly 40 trillion kilometers. The ratio is 8 billion to 1. The improvement from a sailing ship to a jet aircraft represents a speed increase of roughly 100-fold. To achieve the same proportional reduction in interstellar travel time, you would need a speed increase not of 100-fold, but of 1 billion-fold beyond our fastest current spacecraft. And that billion-fold improvement must occur within the constraints of physics that have not changed and will not change. The Atlantic was crossed because the distances involved were compatible with technologies that the physics of Earth allows: wind, steam, combustion, aerodynamics. The interstellar gulf has not been crossed because the distances involved may not be compatible with any technology that the physics of the universe allows, short of discoveries so fundamental that they would represent not an incremental advance, but a revolution in our understanding of nature itself. Such revolutions are possible. They have happened before. But planning a civilization's future around the assumption that they will happen on a convenient schedule is not optimism, it is faith. And while faith has its place, it is not a substitute for engineering. Part of the answer is cultural. Science fiction has spent a century building the assumption that interstellar travel is part of humanity's future. From the earliest pulp magazines through Star Trek, Star Wars, Interstellar, Avatar, and thousands of other stories, the narrative is consistent. Humanity goes to the stars. It is our destiny. The ships are big and fast. The journeys take weeks or months. The destinations have breathable air and interesting aliens. This is a beautiful mythology, and it has inspired generations of scientists and engineers. But it has also created an expectation so deeply embedded in popular culture that many people do not realize it is fiction. They believe, with genuine sincerity, that interstellar travel is an inevitable stage in human development, like industrialization or the internet. Something that will happen eventually, once we get around to it. The physics does not support this belief. The physics supports a much grimmer picture, one in which the distances between stars are not inconveniences to be engineered around, but fundamental features of the universe that define the limits of where life can spread and how fast. The universe may simply not be structured for interstellar civilizations. It may be structured for solar system civilizations, isolated from one another by gaps so vast that crossing them requires resources and timescales that exceed the lifespan of any plausible institutional structure. This brings us to the deepest and most uncomfortable question that Alpha Centauri poses. Not whether we can reach it, but what it means that we almost certainly cannot, at least not in any form that resembles the visions we have been telling ourselves for a century. Consider Proxima Centauri b one more time. An Earth-sized planet. In the habitable zone of the nearest star, the single most accessible potentially habitable world outside our solar system. If any planet beyond the Sun were going to be reachable, it would be this one. It has the shortest possible travel distance. It orbits a star we can study in detail. It is the first place any rational civilization would attempt to visit, and it is functionally unreachable for human beings by any means currently understood. Not unreachable in the sense that it is mathematically impossible. Unreachable in the sense that the combined requirements of propulsion, energy, shielding, life support, reliability, communication, and institutional continuity exceed, by orders of magnitude, anything humanity has demonstrated or credibly planned. Unreachable in the sense that even the most optimistic serious proposals envision a gram-scale flyby probe, not a crude vessel. Unreachable in the sense that even if Proxima Centauri b turned out to be a paradise, a perfect duplicate of Earth with forests and oceans and breathable air, it would remain as inaccessible to human settlement as a city in a dream. There is a word for a place that exists, that you can see, that you can study from a distance, but that you can never physically reach and inhabit. It is not a destination, it is horizon. And horizons have a specific property that makes them different from destinations. No matter how far you walk toward a horizon, it remains the same distance away. It is a feature of perspective, not of geography. You can spend your entire life walking toward it and never arrive. Alpha Centauri may be humanity's horizon, the place that defines the edge of the reachable without itself being reachable. The nearest star, and therefore the clearest possible demonstration that nearest does not mean close, that the stars are separated from us not by distances that will someday yield to better rockets, but by distances that may represent a permanent boundary on the scale of a species. This is not a comfortable conclusion. It cuts against every instinct of a species that defines itself by exploration, by expansion, by the refusal to accept limits. But comfort is not the standard by which we should evaluate ideas about the universe. Truth is, and the truth that Alpha Centauri reveals, is that the universe is structured on scales that do not accommodate human ambition. The stars are not campfires spaced across a dark plain, waiting for travelers to walk between them. They are furnaces separated by abysses so deep and so wide that even light, the fastest thing in existence, needs years to cross the smallest one. There is something important to say here that is not despair and not resignation. It is a recalibration, a corrective to decades of casual optimism that has confused possibility with probability and aspiration with plan. The solar system is not a prison. It is an estate of staggering size and richness that humanity has barely begun to explore. Mars has never been touched by a human foot. Europa's ocean has never been sampled. Titan's methane lakes have never been visited by anything more capable than a single small lander that operated for 90 minutes. The asteroid belt contains resources that could sustain industrial civilization for millions of years. The moons of Jupiter and Saturn present environments so exotic and so scientifically rich that the study of any one of them could occupy generations of researchers. The solar system, from the Sun to the Oort cloud, spans roughly 2 light-years of space. It contains trillions of objects. It offers more scientific discovery and more material wealth than any civilization could exhaust in 10,000 years of effort. The honest path forward is not to mourn the stars we cannot reach, but to recognize, clearly and without sentimentality, the difference between what is real and what is imagined. Interstellar travel, as portrayed in popular culture, fast, routine, crude, is imagined. It is not supported by any demonstrated or credibly proposed technology. It may never be. Interstellar communication, the sending and perhaps receiving of signals across light years, is real and achievable. Interstellar flyby probes, tiny and fast and limited, are conceivable and may become achievable within a century. These are extraordinary capabilities. They are also radically less than what the culture has promised. Alpha Centauri does not owe us a visit. Proxima Centauri b does not owe us a second Earth. The universe does not owe us a frontier that matches the one we romanticize from our own history, when the distances were measured in thousands of miles rather than trillions, and the ships were powered by wind rather than by technologies that do not yet exist. What the universe does offer is a lesson, and Alpha Centauri is its clearest teacher. The lesson is that scale matters. That the distances between objects in the cosmos are not incidental features of the landscape, but defining characteristics of what is possible within it. That the same universe which made stars and planets and the conditions for life also placed those stars so far apart that traveling between them may exceed the capacity of any species that evolves on one of them. That this may not be a flaw in the design, but the design itself, a cosmos built not for crossing, but for contemplating. This is the truth that the nearest star teaches. Not that space is big, which is a platitude, not that we need better technology, which is an evasion, but that the nearest destination beyond the solar system, the closest, the most accessible, the most tantalizing, is already enough to expose the full depth of the separation between us and everything else. You do not need to look at galaxies billions of light-years away to understand humanity's isolation. You need only look at the nearest star, 4.37 light-years. A number small enough to fit in a sentence and large enough to swallow every ship we have ever built or imagined. Voyager 1, our farthest ambassador, is approaching 1 light day from Earth after nearly 50 years of flight. It has covered roughly 1/1500th of the distance to Alpha Centauri. If it were aimed at that star, which it is not, it would arrive in approximately 73,000 years. Every civilization that has ever existed in the history of our species fits comfortably inside that window. Voyager would arrive at Alpha Centauri around the time that whatever lives on Earth has either evolved beyond recognition or vanished entirely. The probe itself would be a dead relic, its plutonium long since decayed to silence, its golden record carrying the voices of a species that may no longer exist. That image is not meant to depress. It is meant to calibrate, to replace the vague optimism of someday we will go to the stars with the precise reality of this is how far the nearest one is, and this is what crossing that distance actually requires. The calibration matters because the stories we tell ourselves about the future shape the decisions we make in the present. If we believe that interstellar travel is just around the corner, we may neglect the solar system that is right in front of us. If we believe that Alpha Centauri is a destination, we may underinvest in the technologies and the institutions needed to survive and thrive on the worlds we can actually reach. Alpha Centauri is not a destination. It is a measurement. It is the distance at which the universe reveals its true architecture. Not the warm, human-scaled architecture of planets and moons and orbital mechanics, but the cold, vast, inhuman architecture of interstellar space, where the gaps between objects are so large that even defining them in familiar units requires numbers the brain cannot honestly hold. The stars are beautiful. They are scientifically fascinating. They are the furnaces that made every atom heavier than hydrogen and helium in your body. You are, in a very real sense, made of Alpha Centauri, because the atoms that compose you were forged in stars like it and scattered by explosions like the ones its predecessors produced. You are connected to those distant fires by chemistry and by history in ways that are profound and real. But you are not connected to them by distance. Distance separates you from them with a finality that no engine currently conceived can overcome. The nearest star is near only by the standards of a universe so large that the word near has lost all relationship to human experience. By the standards of what a human life can cross, what a human civilization can sustain, what a human mission can endure, Alpha Centauri is not near at all. It is the closest example of the farthest thing, the gentlest version of an absolute barrier, the softest sound the universe has ever spoken, and perhaps the wisest thing we can do is hear it clearly, not as a defeat, not as a door slammed shut, but as information, as data about the kind of universe we live in and the kind of species we are within it. A species brilliant enough to measure the distance to the stars and honest enough, if we choose to be, to admit what that distance means. The light from Alpha Centauri left its surface 4 years and 4 months ago. It traveled across 40 trillion kilometers of empty space. It passed through the thin veil of dust and gas that fills the interstellar medium. It entered the solar system, crossed the orbits of the outer planets, passed the sun, and arrived at the surface of your eye at 300,000 kilometers per second. That journey, made at the fastest speed the universe allows, took 4 years. You received that light effortlessly. You did not build anything. You did not burn any fuel. You did not solve any engineering problem. The universe delivered it to you for free, and in that delivery is the final lesson. The universe is generous with information. It sends the light of every star to every point in space without cost or effort, but it is not generous with access. The light comes to you. You do not get to go to the light. 4.37 light-years. The nearest star. The shortest distance. The smallest gap between here and anywhere else among the hundreds of billions of stars in this galaxy. And it is enough.